So, welcome to today's class on probability and information theory. This is an extremely important field of study and a huge field. So, today we shall be trying to kind of concentrate on some of the basic principles which are necessary to understand the design and analysis of ciphers. So, in today's talk we shall be talking about the importance of probability in cryptography, and then discuss about computational security, and then follow it up with some discussions on binomial distributions and its applications, and but the very important birthday paradox, and then conclude with some concepts of entropy and information theory. Now, as we have been discussing that if you remember in our first class that we essentially were trying to understand rather answer the questions to the, we are trying to answer questions of this nature, like how probable is the insecure event. Okay, so you remember that in our example on the coin flipping over telephone, the question was like, what is the probability of Alice to create a x which is not equal to y such that fx and fy are essentially the same. So if you remember that we were the question was like whether Alice is able to choose two different x and y values such that the outcome, which is denoted by fx and fy, are the same. The other question that we tried to address was that what is the probability that Bob can guess the parity of x. So that was the important information, and the question was that whether from the value of fx Bob is able to extract out the information on the parity of x. So therefore, these type of questions will again and again appear in the course of when we are trying to design and also analyze the ciphers, and therefore the theory of probability is quite central to the development of this field. So a good crypto system, as we discussed in the last class, was that it should produce a ciphertext which has got a random distribution. That means that we should kind of look as much random as possible to a distinguisher. So therefore, it should not be kind of detectable, it should not be kind of easily distinguished from a random distribution. So therefore it is, in the entire, so it has to be random in the entire space of the ciphertext message. And the thing is that if it is perfectly random, so let us leave it like perfectly random. We will try to make this notion more and more concrete as we proceed. And the thing is that there should not be any information leakage. Okay, so therefore a lot of terms are being coined out here, like information and also the notion of perfect randomness. We will try to make these things more concrete and more mathematical as we proceed. So but now let us try to kind of understand them intuitively. So it means that when something is like it's perfectly random, so then it essentially is like it's not giving us any extra information, right? So therefore the idea is that it has got zero information content. Okay, so therefore if you remember that we talked about the magic function fx, and therefore if the function fx does not leak any information or any or rather any fact about the parity of x, then we say that it does not leak any information. It does not leak any information. Okay, and therefore this information, or rather the lack of information, is sometimes also referred to as the uncertainty of ciphers. So we will try to kind of measure these terms like perfect randomness, information, and also uncertainty. Okay, and we essentially rely heavily on the theory of probability and also develop the theory of information using these probabilistic notions. Okay. So another important concept, although we shall not be really going deep into this, is the concept of probable security. Okay, so something which is called a semantic security is very central, and it is defined as follows. So remember Alice and Bob, right? So therefore the idea is that Alice essentially encrypts either 0 or 1 with equal probability. So therefore Bob knows that either 0 is encrypted or 1 is encrypted, and the probability of choosing a 0 and 1 is half. Okay, now so therefore Alice encrypts these either 0 or 1 and sends the resultant cipher C to Bob as a challenge. So now Bob has to essentially guess from the challenge without the decryption key that whether 0 was encrypted or 1 was encrypted. Okay, so if Bob is not provided with a ciphertext, then what will Bob do? Bob will simply guess, right? So now when Bob is provided the ciphertext, he should not be able to guess any better than the random guess. Okay, so that's the idea of if he is not able to guess any better than the random guess, then we say that the encryption algorithm which Alice is using is semantically secure. Okay, so therefore if you consider like if you just consider a simple kind of stream cipher, like for example if you just see that there is a kind of message, right, and if I just and what Alice does is that it chooses randomly a key value and it creates a cipher text. Okay, so therefore this message can either be 0 or 1. Okay, so the key also can be either 0 or 1 and it's randomly chosen. So now this particular cipher text is being provided to Bob, and Bob from this notion of from this cipher text value has to guess whether 0 was encrypted or whether 1 was encrypted. So Bob knows from this, if this is the encryption algorithm which Alice uses, that Bob is either receiving M or it is either receiving M bar. Okay, because the key can either take 0 value or 1 value. We are just considering a very simple case. Okay, so now Bob has to guess whether 0 has been encrypted or whether 1 has been encrypted, and if Bob does not have any information of the cipher text, then Bob would have simply guessed. So in this case also, I mean, when Bob is even provided with a cipher text, the probability of Bob being able to guess whether the message is 0 or 1 should even then be close to half. Okay, so that's the idea of semantic security. So now, so therefore Bob or any eavesdropper does not have any advantage over. So that's the idea, that it should not have any advantage over a random case. Okay, so semantic security tries to encapsulate or capture this particular notion. So we essentially have been discussing about something which is called message indistinguishability. That is, I mean the idea is semantic security and message indistinguishability are the same notions. Okay, that is, these notions say that you are, the attacker is not able to distinguish between the encryptions of either a 0 or a 1. Okay, but often, we essentially talk about something which is called a computational security. So if you remember, as we will see that there are two ways you can actually kind of model the attacker. Okay, you can either assume that the attacker is kind of an unbounded adversary, that is all powerful, it has got large access to large amount of resource, and it can do kind of large computations. Okay, so that's the notion of an unbounded attacker. So you can make your security algorithms which are protected against an unbounded attacker. You can try to do that. The other thing which you can do is that you can assume that in today's computational power or today's world, the maximum computations which an adversary can do. Okay, like what is believed in today's thumb rule is that if there is any algorithm which requires more than 2 power of 80 computations, then it is termed as infeasible. Okay, so for example, if I can limit or bound the attacker of today's world by say 2 power of 80 computations, and if we can prove that a particular attack for an encryption algorithm requires more than 2 power of 80 computations, then we are happy as a designer. Okay, so that's the idea of a computational security analysis. Okay, that is, I am not trying to really give you guarantees of security against an unbounded attacker, but we are trying to give you security against a bounded adversary. Okay, an adversary which is bounded by computational power. And the other advantage that you arrive, apart from the simplicity, is that often you will find that when you are trying to give security guarantees against an unbounded adversary, you may end up in an encryption algorithm or a technique which is not practical. Okay, but as we discussed, that we also need practical security, that is, the cipher should be practical. Okay, so therefore, in order to make it practical, it is often advantageous to assume that the adversary is actually not unbounded, but it is kind of bounded. Okay, so therefore that is the notion and the importance of computational security analysis. So we will try to make this idea more clear as we proceed. So therefore we define a crypto system to be computationally secured if the best algorithm for breaking it requires at least n operations, where n is a very large number. Now another approach is to reduce the problem. So therefore this is another approach which is often taken, is to reduce the problem of breaking a crypto system to a known problem, like factoring a large number to its prime factors. Okay, so therefore it is often assumed that factoring a large number to its prime factors is a difficult problem, is a quite hard problem. Okay, so although we do not have real proofs for proving this fact, but the idea is that this particular problem has withstood large number of analyses and withstood a long period of time, and it is believed that it is fairly hard. Okay, so the approach which is taken is that when a given crypto system is given, for example, if I just take the example of an asymmetric crypto system called RSA, and somebody asks me to prove the security of this system, the approach which is adopted is to kind of reduce this problem of proving, or reduce this problem of breaking this RSA crypto system to this known problem. Okay, that is, we do a reduction proof and show that if this problem, and the idea is that if this problem is a difficult problem, then so is the problem of breaking this RSA crypto system. Okay, so these kind of proofs are essentially kind of relative, and they are not absolute, okay, and they are sometimes called proof by reduction. So we also see some examples of such kind of security proofs in our class also. So probability is a good tool, okay, and it's a kind of proof, tool which is kind of helps us to analyze the ciphers, okay. So let us try to make the concepts little bit more well defined. So imagine that, there are some important definitions. One of them is probability space, okay. So the probability space is kind of a fixed set of points which is arbitrary, but it is kind of denoted by S often, okay. So let us consider an example. Like suppose there is an unbiased coin, okay. So the unbiased coin can take two possible values. So therefore we define its sample space to be the values like head and tail. So it can take either head value or it can take either tail value, okay. And then we define an experiment. So the experiment is defined, for example, as follows, like experiment E1 is nothing but the outcome of a toss, okay. So if we assume that this is an unbiased coin, then this experiment, what it does is that it essentially chooses or samples out a point from this sample space, okay. So therefore this result can either be a head or it can be a tail, okay. So it just chooses a point from this head and tail, okay. So similarly you can actually make this example a little bit more complicated, and for this simplistic, for the simple example, I think we can actually understand the concepts, quite well. So therefore, if I just make it kind of a little general, then it will look like this. That is, the probability space is arbitrary but fixed set of points, okay. For example, the head and tail, it could be more than that also, and we denote that by S. And what the experiment does is that it's an action of taking a point from S, okay. So it just chooses a random point, chooses a point from this sample space. So, and we define, this is a sample point which is commonly called the outcome of an experiment. So you toss a coin, it's either head or a tail. So the head or the tail is a sample point of the experiment, okay. So let us try to make it a little bit more kind of complicated. So you have got, not only, two possibilities like head or tail, but what you do is that you toss the coin for 10 number of times, okay. So therefore if you toss the coin for 10 number of times, then there are several possible outcomes, right. So therefore you know that if you toss the coin for 10 number of times, then it could be like it's a sequence of heads and tails, right. So it can be head, tail, 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 and so on till head or something like that, right. So if you denote all, the head by 0 and the tail by 1, you know that there are actually how many possible enumerations or possible outcomes? There are 2 power of 10 possible outcomes, okay. Now if I denote a particular kind of event as saying that the event is like 5 times head and 5 times tail, then it means that from all these sample points I am interested in the probability of one particular event, okay. So this particular event, like this head and tail, can occur actually in certain possible ways, right. So therefore it can be so essentially we can actually compute the number of times exactly 5 times head falls by simply computing 10 choose 5, okay. So therefore the probability of this event, that is the probability of this event that there are 5 heads, will be essentially nothing but 10 choose 5 divided by 2 power of 10, okay. So this way of computing the probability is something that we have quite seen, okay. So therefore if I kind of make it or rather define it, this is the classical definition of probability. That is, if there is an experiment which can have, which essentially yields 1 out of n possible equally probable points, and that every experiment must yield a point, of course, and let m be the number of points which form the event E, then the probability of an event E is defined as the ratio of m and n, okay. So there is a statistical definition also. Now why do we require this statistical definition is something we can easily understand, that for example, if I tell you that there is an unbiased coin, and if I tell you that the probability of a head is half, right, then that means that does not mean that if I toss the coin for 2 times, then one of them will be a head. It does not mean that. What it means that is that if you keep on tossing the coin for a large number of times, then the half of that number of times you toss will be, at least approximately half will be head, right. So therefore the notion of probability actually holds in reality when you kind of repeat the experiment for a large number of times. So there is actually a notion of statistics involved in the way we are defining probability, okay. So therefore suppose there are n experiments and these are carried out under the same conditions in which the event E has occurred mu times, okay. So for a large value of n, so that means this is important, that is if I repeat the experiment for a large number of times, then the event E is said to have the probability which is denoted by probability of E approximately equal to mu by n. Okay. So therefore, what I do is that instead of computing the probability by finding out the outcomes and the number of possible ways these outcomes can come, what we can do is that we can keep on repeating the experiment. Okay. So we find that if we have actually repeated the experiment for a large number of times, and out of the mu number of times a particular event has occurred, then we can fairly approximate its probability by the ratio of mu by n. So this is a statistical definition and often useful for analysis. Some of the very elementary probability rules are as follows. Now you know this, but this is a kind of recapitulation. That is, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Okay, and if they are mutually exclusive, then we know that probability of A intersection B works out to 0, and therefore probability of A union B is equal to probability of A plus probability of B. Now this particular rule is often handy in giving us upper bounds of the probability of A union B, because we can say that probability of A union B will be lesser than equal to probability of A plus probability of B. Okay, because this probability is definitely greater than equal to 0. So, and then we define we know the definition of conditional probability, where probability of A given B. So this probability means that the event B has occurred. If we know that the event B has occurred, what is the probability of A? Okay, and the way it is being computed is probability of A intersection B divided by probability of B. Now if A and B are independent, then what is the probability of A given B? That is, it's same as probability of A, right? Because A does not really depend upon the outcome of B. So the probability of A intersection, rather A given B, becomes equal to probability of A when they are independent, and therefore probability of A intersection B becomes equal to probability of A multiplied by probability of B. So that is this. That is, if A and B are independent, then probability of A intersection B is nothing as probability of A multiplied by probability of B. Then there is a very important law which is known as the law of total probability. If there are if there are n events like E1, E2 and so on till En, and if the union of them is a sample space S, and if I know that they are mutually non-intersecting, that is Ei and Ej cannot take place together, and therefore the intersection of Ei and Ej is equal to the null set, and then for any event A, we can say probability of A is equal to, so what we do is that we multiply probability of Ei, that is the probability that the ith event has occurred, with probability of A given Ei, that is probability of A given that the event Ei has occurred, and then take a sum over all possible I values. Okay, so the I runs from 1 to n. Okay, so this is also a very handy rule for doing our computations. So then we know that when we are talking about cryptographic, we are essentially not talking about a continuous probability space. We are actually talking about discrete space. Okay, so therefore in this case, the total possible sample points can actually take some discrete possible outcomes. Okay, so it can run from x1 to say x2 like till x hash s. Okay, hash s is nothing but the number of elements in the sample point. Okay, and what we do is that for each of these sample points, we actually define a probability. Okay, so first of all, we define something which is called a random variable, and and then we say that this particular random variable can take such and such possible values, and then we try to assign a probability for this random variable. Okay, so you see that if there is a discrete space S which has got a countable number of points like x1, x2 until so on till x hash s, and then a discrete variable, what we do is nothing but a numerical result of an experiment. Okay, so it is a function which is defined on a discrete sample space. Okay, so for example, if I say that for an example of a discrete variable could be like if there are some points like x1, x2 and x hashes. So suppose we define a function like, suppose the value of x1, suppose imagine that all of them are binary values, like suppose there are 4-bit binary values, so there could be 16 possible such numbers like 0, 0, 0, 0, 0, 0, 0 to all ones, to all 4 ones, and we say that we are interested in finding out the probability that all of that is the numbers are, for example, even. Okay, so we know that what we will do is that from all these possible values, we will try to find out those binary values which end with 0. Okay, so we define an experiment, and therefore this is the function which is defined on a discrete sample space, Okay, so what we do is that now I mean let S be a discrete probability space and X be a random variable. So X is a random variable, and we actually start assigning probability values for these random variables. Okay, so this random variable X can actually take some what are the possible values this random variable X can take? It can either take x1 value, x2 value, or till x of x hashes. Okay, and what we do is that for each of these possible values of the random variable, we assign a probability. Okay, so we say that X can take a value, say the random variable X can take the value of x1 with the probability of say p1. The random variable X can take the value, take the value of x2 with the probability of p2. The random variable X can so on take the value of say x hash s with the probability of p hash s. Okay, so we can define the probabilities like this. So these probabilities will be discrete probabilities, and it needs to satisfy two important properties. One of them is that each of these probability values should be greater than or equal to 0, that is, they should not be negative, and the other thing is that the summation of all these probabilities should be equal to 1. Okay, so therefore this probability essentially is, this should satisfy these two properties. Okay, and we can actually say that these probabilities are are essentially a map from the sample space S to the set of real numbers, because the probability values are essentially nothing but real numbers which lies between 0 and 1, both sides included. Okay, so this is so these are actually the individual probabilities, and this should satisfy these two important properties. So one of the very frequently used distribution is something which is called a uniform distribution, and we know that in this case all the values like x1 till x hashes are equally probable. So the random variable X can take x1 or x2 or x3 or x hashes with the same probability, and the probability is nothing but 1 divided by hash s. Okay, the next is said to follow a uniform distribution, and it is often denoted like this, that is, suppose I say that P choosing uniformly from S, so therefore it means that choose P uniformly from S. Okay, so this is a very common notation which is useful. So then we actually define a very important distribution which is called a binomial distribution. So it says that suppose there is an experiment and it has got two possible values or possible outcomes, like it could be either a success or it could be either a failure or a head or a tail, and then we repeat the experiments and repeat the independently such experiments, and these are called Bernoulli's trials. Okay, Bernoulli trials. And if I denote the probability of a head to be p and the probability of a tail to be 1 minus p, of course, because the head and the tail together, if I add these two probabilities, should be equal to 1. And what is the probability that there are k successes in n trials? Okay, so therefore I repeat the experiments, and the question is, what is the probability that among the n trials there are actually k number of successes? And we know that this actually works out to this, that is n choose k, which means that we choose the k success points, and then for k success points the probability will be actually p p to the raised to the power of k, and since the other points are failure points, so they should be also multiplied by 1 minus p whole to the power of n minus k, because there are n minus k failure points. Okay, so this gives us a number of ways of this gives us the probability that there are k successes in n trials. Okay, now if a random variable y takes values like 0, 1 to n, okay, so therefore 0, 1 to n means if I say that this success, that is the number of successes in n trials, and I denote that by a random variable, then this random variable can take values from 0, that is, it can be that there are no successes, to n, that is, all of them are successes. Okay, so therefore the random variable y can take values from 0 to n, and for values which lies between 0 to 1, that is for p, the probability that y, and we say that the probability that y is equal to k, which means that there are k successes, is given by n choose k, p to the power of k multiplied by 1 minus p whole to the power of n minus k. If this random variable satisfies this probability distribution, then we say that y follows binomial distribution, and this is a very common and useful distribution. Okay, and then we talk about something which is called a law of large numbers, very useful. So it says that if we repeat a trial for a large number of times, where n is suppose infinity, n tends to infinity, and we note the number of successes. Okay, so after a point the number of successes will actually remain a constant and will be actually computed by something which is called the expectation, and the expectation is nothing but the number of times you are repeating the experiment multiplied by the probability of success. Okay, the p is the probability of success. So in that case, I mean, this is often referred to the expectation of the random variable. So as it is told here, the limit n tends to infinity, the probability that epsilon n by n minus p is lesser than a very small number, small but fixed number, and this probability is equal to 1. Okay, so therefore this is something which is called the law of large numbers, which says that if you repeat the experiment for a large number of times, then essentially you will find that the number of times you get the number of successes will actually be found out by computing the expectation of the random variable. Okay, so the expectation of the random variable is kind of gives us an estimate about the number of times a success of an experiment will occur if I repeat the experiment for a large number of times. Now this particular law and the concept of binomial distribution has got a very important application in the field of cryptographic analysis. Okay, so for that, let us kind of consider this particular result. Okay, so therefore it says that let epsilon be an event in a probability space X with probability of epsilon is equal to being equal to p, and p is greater than 0. And what we do is that we repeatedly perform the random experiment X independently. Okay, so what we do is that, so what we are saying here is this, that is there is an event epsilon. So epsilon is an event, and there is a probability space X. Okay, so what we are doing is we know that the probability that epsilon occurs, that is this particular event occurs, is actually given by p, where p is some non-zero value. Okay, it's greater than 0. So what we then do is that we kind of repeat this experiment, okay, again and again. So we repeat, I mean, we do the experiment X once, we do the experiment X twice, and what we need is that we need to find out the expected number of experiments, of X until epsilon occurs the first time. Okay, so what we need is that we need the expected number of experiments of X until epsilon occurs the first time. So what we are interested is that we are interested in a particular event. Okay, and what we know is that we know the probability of this event. Okay, and we need to find out the number of times we would like to repeat this experiment until we first get the success. Okay, the success is defined as the fact that this event epsilon occurs. Okay, so what is, I mean, how do we compute that? Okay, and what we say is that if this g is nothing but the random variable, it says that this is the expected number of times, this is the expected number of experiments of X, okay, until epsilon occurs the first time. Okay, and what we will do is that we will try to give a proof or develop a proof that this expectation Ej is actually given by the reciprocal of p. Now what is the impact of this result? Okay, so suppose there is an attack. Okay, suppose you develop an attack and you say that the probability that this attack works has a complexity of say 2 to the power of minus n. Okay, so that means you say that you can actually find out the fact that you can actually find out the particular kind of a particular key is a 2 power of minus n. Okay, so then this particular results gives us a kind of indication that if I repeat the experiment or if I repeat the attack for 1 by 2 to the power of minus n number of times, that is 2 to the power of n number of times, then I should get the attack working at least once. Okay, that is after 2 to the power of n operations I should get the attack to work. So therefore that means that if, for example, if I say you that, for example, in AES, if I say you that there has got 128-bit security, and if I tell you that, okay, therefore the probability that you can actually make the attack work is 2 power of minus 128, then immediately you know that if I repeat the experiment for 2 to the power of 128 number of times, which is very huge, you will get one success. Okay, so therefore this actually gives us a nice indication to find out the experiment. I mean, so if there is a kind of property which you can exploit for an attack, it gives you an estimate about the number of times you need to repeat the experiment to get a success once. Okay, and the proof of this is actually quite simple, and it follows from the binomial distributions notions. And the idea is as follows: like what you do is that you find out probability of g equal to the value that g is equal to t, and you know that g equal to t means that the I mean what we are computing here is that the success occurs at the tth number of times. Okay, that is, it occurs at the tth instance, which means that the previous previous experiments, right, like till t minus 1 has been failures. So therefore this probability can be computed by 1 minus p, raised to the power of t minus 1, because they were all failures, multiplied by p. Okay, and therefore the expectation of expectation of g by using the law of large numbers will be equal to this probability multiplied by the number of times you are repeating the experiment. Okay, so therefore what you are doing is that you are repeating this for t number of times, and therefore you multiply this by 1 minus p to the power of t minus 1 and multiply that by p. Now you note that this particular t can be anything, right? It can go from t equal to 1 when the first time when you are doing the experiment to t equal to infinity. Okay, so it can be a summation like this. Okay, and then we are actually not going into prove this, but you can follow that this is actually equal to minus p differential with respect to p of sigma 1 minus p whole to the power of t. Okay, so this will work out like this, where t runs from 1 to infinity. Okay, you can check this, that it actually gives you the same value. Okay, so then that follows from simple differential calculus. Okay, if you differentiate this, you will get this, right? So now this means that if I take this sigma, then this is nothing but minus p ddp. Okay, and I would like to add this sigma, so there is 1 minus p to the power of 1 plus 1 minus p to the power of 2 plus 1 minus p to the power of 3, so on till 1 minus p to the power of infinity. Okay, so you note that since this value is less than 1, this sigma actually converges, this summation actually converges, and what we get is ddp of 1 by p minus 1. Okay, and this actually works out to 1 by p. Okay, so therefore from here we actually get an estimate about the number of times we have to repeat the experiment, so that we actually get this experiment to work. Okay, so therefore it is important to note this result, because this actually gives us an idea about if there is an experiment's success defined, experiment's success probability defined, then from there to get an estimate about the number of times we need to repeat the experiment to get that success, or to get that event. Okay, so then we come to the next important concept in today's class, which is called the birthday paradox. Okay, and birthday paradox is again quite central to the idea of analysis of ciphers. So consider a function f, which is a mapping from x to y, where y is a set of n elements, and consider that this class of students form x. Okay, that is, let y denote the birthday. Say 15th September is the birthday of a person x. Thus y is the so therefore there are two things here. One of them is x and the other one is y. Okay, so that is essentially, we are essentially considering a mapping from x to y. So let us consider this class of students from x. Like, let us consider that in this class there are x students. Okay, that is, there are x students, and let us consider that there are possible number of birthdays can be 365. So there are 365 possible days of birthday. Okay, so let us choose a person, say A, and we know that A will be mapped to one of these dates from this 365. Okay, so if there is another person, then he or she will be mapped to another particular day among these 365s. Okay, so the question is, that is, if you consider, for example, what we are essentially considering is that we are considering the fact that there can be two persons, or say another person, so who essentially are born on the same day. Okay, so there is a collision of these two birthdays. So we can say that the problem is like this, that is, we can abstract out this problem as this, that is, choose k pairwise distinct points from x uniformly and define collision to be the event for I not equal to j, where fxi is equal to fxj, and we check for the corresponding fxi's when a collision occurs, and clearly the probability of a collision increases if k is increased. That is, if I choose large number of points, that is, if I choose large number of students from the class, then the probability of that they are born on the same day also increases, right? The question is now, what is the least value of k? So we are actually interested in the least value of k, so that the probability of a collision is more than say epsilon. So we would like to give a lower bound of the probability. Okay, so first of all, you understand there are two important things. One of them is this least value, and then we are actually giving a lower bound of the probability. Okay, so why are we choosing the least value of k? Because if I start increasing this k, and if this k is quite large, then this probability will obviously increase, and the probability of collision will obviously increase. But what we are interested is in finding out what is the least value of this k, okay, so that this probability, so that this collision occurs. And then we are actually also trying to give a lower bound of this probability, that is, the probability should be at least this much. Okay, so we would like to give an answer to this question. Okay, so in talking about in the birthdays term, like we are actually interested in finding out what is the number of students which should be in that class. Okay, that is, what is the least number of students which should be in the class, so that the probability that two of them are born on the same day is say more than half. Okay, so that is, I am interested in finding out what is the least size of the class, so that there are two students at least who are born on the same day, and the probability of this fact is more than half. Okay, is more than or greater than or equal to half. So we can actually compute this quite easily, and we can do this as follows. Like the probability of no collisions, let us find that first in among these k persons. Okay, so we know that if there are k persons, okay, that is, if there are kind of k persons in the class, and let us consider that this person is mapped to a particular date, that is, he is basically born on the same day. So if you are considering the probability of no collisions, then it means that the second person should not be born on this date, right? So that means from 1 by 360, from 365 days, he can be born on 364 days. Okay, so that is, this is 364 divided by 365, or that is 1 minus 1 by 365. Okay, what about the second person, a third person? The third person cannot be born on this date or this date. So therefore his probability will be 1 minus 2 divided by 365. Okay. So similarly, if I consider the last person, that is this person, then his probability will be 1 minus k minus 1 divided by 365, because there are k persons in this set. Okay, I am considering this least size of the set. Okay. So therefore this probability, and all of them are independent events, so that therefore the probability of no collision among these k persons can be found out by this, right? That is, I multiply 1 minus 1 by 365 with 1 minus 2 by 365 with 1 minus k minus 1 by 365, and so on. And therefore this is like nothing but the product of these probabilities. Okay. Now for a large n and a small x, okay, we have got this approximation, that is 1 plus x by n is nothing but e to the power of x by n. So therefore a large n and a small x, this holds. So if I use this approximation, then this product, or this product of 1 minus I by 365 can be approximated as each of these terms is substituted by e to the power of minus I divided by 365, and then we try to find out the product of these terms. Okay, and this actually works out to e to the power of minus k into k minus 1 divided by 730, because when we are doing a product of these terms, in the powers we are doing actually a sigma. So if I do this sigma, then this sigma of minus I to the power of 365 minus I by 365 will work out as this, right? See, what we are doing is this, right? That is I equal to 1 to k minus 1, and we are multiplying like 1 minus I by 365. So that approximately, by using the approximation, is like I equal to 1 to k minus 1 into the power of minus I by 365. Okay, so now when we are doing this product, then this means that what we are doing is e to the power of minus I by 365, and then actually we are doing a summation here, right? So that means that it is kind of like e to the power of 1 by 365. If you take common, it is like 1 plus 2 plus so on till k minus 1. Okay, so that means that this is nothing but e to the power of 1 by 365 into k minus 1 by 2. Okay, there is a minus out, so this minus will come out. So minus 1 by 365 into k minus 1 by 2. Okay, so that is nothing but e to the power of minus k into k minus 1 divided by 730. Okay, so suppose we say that this probability, so this is the probability that there is no collision. So what is the probability that there is at least one collision? that is simple, right? That is 1 minus e to the power of minus k into k minus 1 divided by 730. And if I say that this probability should be at least equal to 0.5, then we can actually get an estimate of this k by computing, or rather equating this to 0.5. Okay, that means we are trying to say that this probability actually should be greater than or equal to 0.5, but in order to compute the value of k, let us assume that this k, let us equate this with 0.5 and find out an estimate of k. We can actually see this, and I'm not really going into this. That is, you can find out, like, you can do these calculations like this. That is 1 minus k e to the power of minus k into k minus 1 divided by 730 is equal to 0.5, and therefore k into k minus 1 divided by 730 will be equal to ln 2. Okay, so therefore you can actually do this, right? So therefore what you can do is that you can bring this like this, like e to the power of minus k into k minus 1 by 730 will be equal to 0.5, and then if you take a log on both sides, then it works out to like k into k minus 1 by 730 is nothing but ln of 2, and therefore you can actually get k square minus k will be equal to 730 into ln 2. Okay, and therefore if you neglect k with k square, then k will be roughly equal to square root of 730 ln 2, and that will be approximately 23. So which means that if there are, if there is a random room of 23 people, then the probability that there are 2 persons with the same birthday is 0.5. So this actually seems to be a paradox. Why? Because what if I ask you, like, what is the probability that there are 2 people who are born on the same date? Is actually very small, right? It is actually 1 by 365, so that's very small number. But we see that in a random room of 23 people, the probability that there are 2 persons which are born in the same birthday is actually quite high. It's actually 0.5, and we will see that if I increase this 23 people to little larger, then actually this probability shoots up quite fast. So now this is a very kind of specific example, but you can actually work out a more general case. Okay, that is, instead of 365, you can have maybe 2 to the power of n possible outcomes, and then try to find out the estimate of k. But what we will find is that this k will roughly be proportional to the square root of total number of possible ways. So which means that if you kind of need to do a brute force search of, say, 2 to the power of n possible values, then if you apply the birthday paradox, then this gives you an estimate that after 2 to the power of n by 2 random searches, there should be, there is a high probability that 2 of them will actually result in a collision. So this particular paradox, or this particular analysis, is used again and again to do the analysis of ciphers and develop its security proofs and other stuff. So there are a lot of applications, like deciding the bit length of the hash function. Digital signature schemes have to be kept more than, say, 128 bits. It is used for doing cryptanalysis like index computation, which are algorithms to solve something which is called the discrete logarithms problems. So we will actually try to find out a very interesting application of the birthday paradox. So it's something which is called cycle finding algorithms. Okay, so suppose there is a kind of a linked list which is very large, and I am interested in finding out a cycle in the linked list. Okay, so this is one question that may appear. Okay, so one way of doing that is kind of go through the entire linked list and kind of store a huge amount of data, and then once you see a repetition, you report a kind of cycle. Okay, but can we do better than that? Because what the birthday paradox says is that if you choose the elements in this list at random, and if there are kind of 2 to the power of n possible elements, okay, then after 2 to the power of n by 2 possible searches or possible points, there is a quite high probability that 2 of them will actually lead to a collision. Okay, that is what I am saying is this. That is, so suppose you actually keep on just arbitrarily randomly choosing the points. Okay, then you will find that after some point it may happen that the next, you keep on kind of computing, and you will find there will be a resulting collision. Okay, the moment you get a collision, you know that there is a cycle. So consider a function f from s to itself. Okay, that is, what you do is that you start from x, then what you do is that you start from x0, so x0 could be here, and then you generate a sequence by recursively as follows, like xi plus 1 is equal to ff xi, and you just keep on computing this value. the goal is to find a collision such that xi and xj are same, okay, that is xi and xj are resulting in the same value. So we can actually have a birthday approach, that is, note if f is random, then the birthday paradox comes into play and we expect a collision after 2 to the power of n by 2 points if s has got n points, 2 to the power of n points. So assume that the cycle structure is like this, that there is a tail from x0 to xs minus 1 and there is a loop from xs to xs plus l, okay, that is from x0 to xs minus 1 you come here, this is the tail, and then from the next one, that is xs to xs plus l, there is a kind of cycle, okay. So that means this cycle has got a length of L, okay. So now the question is, how do you detect this cycle? So one way of doing this could be a tree based approach. So what you do is that you start storing the sequence elements in a binary search tree as long as there is no duplicate, okay. So you keep on adding them to the tree and as long as there is no duplicate. Now therefore the first duplicate occurs when xs plus L is to be inserted, because there is already xs which is inserted into the tree, and the moment you get to insert xs plus L, you know that there is a kind of duplication and therefore you report a collision. Now what is the time complexity here? We know that if you are using a binary search tree, then the complexity will be around OS plus L log of S plus L. But what about the space complexity? The space complexity is still OS plus L. So that means that although the runtime is optimal, because actually you cannot do better than this in terms of time, but the space requirement is quite high, okay. That is, this could be an exponential and large, this could be quite a large value, okay. So therefore the question is, can I make the space requirement less? A very interesting technique is being adopted for finding out the cycles, a very simple algorithm I will discuss here. It's called Floyd's cycle finding algorithm, and it works out as follows, and we will see an application of this in context to factorization when we discuss about factorization. So you see that what we do is that we set y0 is equal to x0 and we compute another sequence yi plus 1 as f of yi. So instead of applying once f, I am applying twice f. So the input initial sequence is x0 and we set the maximum iterations is m. So what we do is that we start x is equal to x0 and y is equal to x0. So we start at the same point, and then for all these possible iterations that we have set as the maximum value, we compute x is equal to fx and we compute twice for y, okay. So that is, we apply f twice and we obtain the points. So if we get a collision at some point, like if x and y is same, then we say that there is a collision between I and 2i, because you see that if you say that this x sequence is at a point I, then the y sequence is actually a point 2i, okay. And if you get so, then you actually say that okay, there is a collision, otherwise you say that there is a failure, okay. And you will see that actually you have got a quite good chance of actually getting a collision, because of the simple fact that this particular length, that is the length of the cycle, will actually divide 2i minus I, okay. We will actually divide this 2i minus I. So this is actually a very useful algorithm, and it is often useful, it is often useful for doing analysis. And one of the reasons is that I can, for example, if you consider the cycle, like it's like this, right, it looks like a row. So if you start from x0 and you come till xs, so this is, suppose this point is xs minus 1 and this is xs, and you keep on obtaining, and then this is again xs plus L. So therefore the length of the cycle is L, okay. So therefore there are some L successive points here, and therefore you know immediately that there must be, from the L successive points, there must be one point here, call it I dash, okay, which is divisible by L. So there are L successive terms, so therefore there must be one term I dash, okay, which L divides, okay. So therefore if L divides I dash, then that means that L divides 2I dash minus I dash, okay. So that is I dash itself. So that means that if you kind of compute the series of x like this, that is, if you compute xi dash and if you compute x2i dash, then that means that you will essentially find out, if you are basically computing these values, then you may not be able to find out the first time this particular collision occurs, but you will find out a successive point when the collision occurs, okay. So therefore you will definitely get that will essentially give you this collision, which will lead to the detection of this cycle, okay. So we will see this in one of our future classes when we discuss about factorization of factorization. So then we conclude our talk with some notions of information measurement. So let us consider a language of n different symbols a1 to an, and let us assign independent probabilities like probability of a1, probability of a2, and so on till probability of an. Now these probabilities must satisfy that sigma of these probabilities will be equal to 1. Okay. So what is the entropy of the source S? The entropy of the source S is defined as Hs is equal to sigma of probability of ai multiplied by logarithm of 1 by probability of ai base 2. Okay. So this actually gives us the number of bits which are required per source output. Okay. So therefore this notion of entropy is often useful for computing the information content. So let us consider some examples. If S outputs a1 with probability of 1, then Hs will be equal to 0 because your probability is equal to 1. So therefore if I plug in probability 1 here, then this logarithm computes to 0, and therefore this Hs is 0. Okay. But if S outputs n symbols with equal probability, that is the probabilities are 1 by n, that is S is the source of uniform distribution, then this Hs will compute to 1 by n sigma of logarithm n base 2, and that is nothing but logarithm n base 2. Okay. So therefore Hs can be thought of as the amount of uncertainty or information in each output from S. So consider like if you have got kind of a binary sequence of values, like if there is an n bit length, okay, then there are 2 to the power of n possible values here, and all these 2 to the power of n possible values can be chosen. Okay. And therefore the probability of a particular sequence is nothing but 1 by 2 to the power of n. So in that case the number of bits which are there are, in order to find out the value of x, is actually n. So therefore you need to kind of ascertain these n bits in order to find out the value. Okay. So therefore you do not so that is essentially the amount of uncertainty or the amount of information you need to find out the value. Okay. So therefore and if we think of the previous example, that is if S outputs a particular a1 with a probability of 1, that means you know that there is no information, there is no uncertainty. Okay. So therefore the uncertainty is 0. So therefore in this case the uncertainty was 0, but here the uncertainty is logarithm n base 2. Okay. That means if I say that this n, right, then if S outputs n symbols, and if n is equal to say 2 to the power of capital N, then which I denote by n bits, then this logarithm will work out to be n. So that means that I need to, there is an uncertainty of n bits which is there in Hs. Okay. So there is an uncertainty of capital N bits in the source S. Okay. So therefore this notion of entropy gives us an idea about uncertainty or information. Now I will leave you with a question, that is suppose that there are there is a 4-digit pins and which are randomly distributed. How many people must be in a room such that the probability that 2 of them have got the same pin is at least half? Okay. So you can immediately understand that you should be applying birthday paradox to solve this problem. So the references that I have used are Wenbo Mao's Modern Cryptography, Theory and Practice, and some of the things which I have taken from Algorithm Cryptanalysis by Antoine Zoux, and by Bookman, Introduction to Cryptography. It's a Springer book. So in next day's topic we will take up the topic of classical crypto systems and discuss about some classical methods of doing cryptography.